Problem 1. Find the equivalent inductance of the following circuit. Each inductor has an inductance of 4 henries. Please pause the video and attempt the problem. So if we look at these inductors, we can see that there are 4 inductors, and at the start, the only ones that we can combine are these two. These two inductors are in parallel because they're connected at this node and at this node. So two inductors in parallel, we use the equation 1 over L equivalent is equal to 1 over L1 plus 1 over L2. Both L1 and L2 are 4 henries, so 1 over 4 henries plus 1 over 4 henries is 2 over 4 henries, which we can reduce to 1 over 2 henries. And remember, that's not the inductance, that is 1 over the inductance. So the inductance itself is 2 henries. And that's the inductance of these two combined. Next step, we take this combined inductor from these two and add it to this one. This combined inductor and this inductor are in series because once we combine these two, they exclusively share this node. So for two inductors in series, we can use L equivalent is equal to L1 plus L2. So L1, that's this combined inductor, is 2 henries. L2 was this one, which was 4 henries. 2 henries plus 4 henries is 6 henries. Finally, this whole branch has been reduced to a single equivalent 6 Henry inductor. It is in parallel with this inductor. Again, they share these two nodes. So again, we use the formula 1 over L equivalent equals 1 over L1 plus 1 over L2. L1 is going to be the equivalent 6 Henry inductor. L2 is going to be the 4 Henry inductor. To add them together, we should find the least common denominator. The least common denominator of 1 over 6 henries and 1 over 4 henries is 12 henries. So 1 over 6 henries becomes 2 over 12 henries. 1 over 4 henries becomes 3 over 12 henries. And add them together, you get 5 over 12 henries. Again, that is 1 over L equivalent, so the last thing we need to do is invert that to say that L equivalent is 12 over 5 henries, which is equal to 2.4 henries. Question number 2. How much energy is stored in the inductors after a long time has passed? Take R1 is equal to 4 ohms, R2 is equal to 12 ohms, R3 is equal to 5 ohms, V is equal to 12 volts, L1 is equal to 2 henries, and L2 is equal to 3 henries. Please pause the video and attempt the problem. So the formula for energy stored in an inductor is U is equal to 1/2 Li squared, which means we need to find the current in these inductors. Now, one hint we've been given is that a long time has passed. Once a long time has passed, an inductor cannot be changing. The formula for inductor is voltage across is equal to di dt times L. After a long time has passed, the current must be at steady state, so di dt must be 0, which means the voltage across the inductors is 0. So we can almost think of those inductors as being shorted out after a long period of time, which would make the equivalent circuit this right here. Now we do want to find how much current is going through this branch and how much is going through this branch. So we can analyze this circuit right here. Now we have a number of ways we can do this. We can find equivalent resistances, we can use Kirchhoff's current law, we can use Kirchhoff's voltage law. I am going to use Kirchhoff's current law, or nodal analysis. Recall that for nodal analysis, we select one node to be ground, set the other nodes up as unknowns, and apply Kirchhoff's current law to determine how much current is going through each branch. Now in this circuit, if I set this node down here to be 0, because of the voltage source right here, I can say that this top node is equal to 12 volts, which means it's only this middle node that is unknown. So if we call that the voltage of that middle node Vm, we can set up the Kirchhoff's current law equation as Vm minus 12 volts over 5 ohms, i.e. the current coming out of this branch, plus Vm minus 0 over 4 ohms, which is the current coming out of this branch, plus Vm minus 0 over 12 ohms, the current coming out of this branch, equals 0. Now we have a bunch of different denominators, so the least common, the least common multiple of 5, 4, and 12 is 60. So let's convert each of these to being over 60 ohms. So this term needs to be multiplied by 12. That gives us 12 Vm minus 144 volts. This needs to be multiplied by 15, so that gives us plus 15 Vm. And this needs to be multiplied by 5, so that gives us plus 5 Vm. And since everything is equal to 0, it doesn't matter that it's over 60, so we can discard that. We combine like terms, we're left with 12 Vm plus 15 Vm plus 5 Vm, or 32 Vm, minus 144 volts equals 0, which gives us Vm is equal to 4.5 volts. If this node is ground, then this node is at 4.5 volts. We can then use Ohm's law, which says V equals IR, to find how much current is going through each of these two resistors. So each of these two resistors has a 4.5 volt voltage drop across it. So for R1, the resistance is 4 ohms. So 4.5 volts divided by 4 ohms is 1.125 amps. And for this one, R2 is 12 ohms. 4.5 volts divided by 12 ohms is 0.375 amps. Now that we have these currents, we can use the formula U equals 1/2 Li squared. For inductor 1, we use current 1, because inductor 1 is in series with resistor 1. So 1/2 times the inductance, which is 2 henries, times the current, which is 1.125 amperes squared, is equal to 1.266 joules. For inductor 2, that's in series with resistor 2, so we can use the current in resistor 2 as the current in inductor 2. And the energy is therefore 1/2 times the inductance of inductor 2 times the current of inductor 2 squared, or 1/2 times 3 henries times 0.375 amperes squared, which gives us 0.211 joules.